to the lecture for Class 4 in Artificial Intelligence. And this covers the reading in the Russell and Norvig text, Chapter 8. And we're going to be talking about first-order logic. So we'll look at why we're going to use first-order logic. We'll look at the syntax and semantics of first-order logic. We'll try some out, sentences in first-order logic, and we'll look at representing the Wumpus world in first-order logic. And I should add that FOL, at least when I took it as a subject, is called first-order predicate calculus, or FOPC. So whether you call it FOL or FOPC, it's the same kind of representation in a reasoning system. So far we've been looking at propositional logic, and there's some really good things about propositional logic. First, it's declarative. The expressions correspond to facts, and we can just assert the facts. Second, it allows for partial, disjunctive, and even negated information, which is often not possible in many data structures and databases. Third, propositional logic is compositional. That is, if you have an expression, a sentence like there's a breeze in square 1-1 and a pit in 1-2, the meaning of that is derived from the meaning of B11 and P12 through the AND operator. And fourth, meaning in propositional logic is context independent. That is, B11 and P12 always have the same meaning. In natural language, on the other hand, meaning depends on context. So, for instance, if we have a piece of text where you've got the word lead, you really need to know the context in order to know whether it's the verb lead or the noun led. On the other hand, the problem with propositional logic is that it has very limited expressive power. So, on the one hand, you've got natural language, which has immense expressive power, and in propositional logic, a simple sentence in English, something like pits cause breezes in adjacent squares, has to be represented by writing one sentence for each square, and that's obviously just way too cumbersome. So we're going to use first-order logic. And as I mentioned the other day, the good news for us is that first-order logic is the logic underlying the Prolog programming language. So how does first-order logic differ from propositional logic? Well, propositional logic, as we said, assumes the world contains facts. However, first-order logic, like natural language, assumes the world contains other things, objects, that is, people, houses, dogs, cats, individuals, and so forth. It also has relations like red, round, brother of, bigger than, and so forth. Now, we were able sort of to fake relations syntactically in propositional logic, but in fact, what was a relation really was just a fact repeated multiple times with different values. It was just different facts that happened to have similar representations. And first-order logic has functions. So it's got things like father of, best friend of, third inning of, and so forth. And of course, the fact that you've got objects, relations, and functions allows us to express concepts that are much richer than those in propositional logic. Well, there are other logics too, and this little table helps us place propositional logic and first-order logic relative to other logics. So propositional logic basically says that in the world there are things like facts. And what we know about the truth of those facts is that they can be true, false, or unknown. In first-order logic, you've got facts, objects, relations, and again, they can be true, false, or unknown. Unknown in the sense that it is not in the knowledge base, and so we don't know whether it's true or false. Now, prologue makes the practical choice that if it's not provable, it's false. But that's a choice. Temporal logic, very useful, and we'll see a little bit of that in this lecture, has to do with facts, objects, and relations, but adds the concept of time. So facts might be true, a fact might be true at time t0, but not true at time t1. Probability theory has facts, but degree of belief. That is, we're maybe less than certain that the fact is true. And finally, fuzzy logic, which is something that our faculty here know a great deal about, has facts plus degree of truth, and basically it's related to interval computation. We're not going to deal very much with probability theory and fuzzy logic in this class because you've got lots of other opportunities to learn about those here in the UTEP CS department. So let's turn to the syntax of first-order logic. There are things that are constants, so you might have a person like King John, the number 2, the University of California at Berkeley, and so forth. There are predicates like brother, which we really mean brother of, greater than, and so forth. There are functions like square root or left leg of a person. There are variables. There are connectives, logical connectives, and or and implies and so forth, not. Equality, and there are quantifiers, namely for all and there exists. Now, when we're dealing with first-order logic as a logical system as opposed to a programming language, our constants start with capitals, and our variables start with little lowercase letters, and so when we see that, we know we're dealing with sort of first-order logic as a more theoretical thing. And when we get to programming, it's just exactly the opposite of prologue. Constants start with a lowercase letter, and variables start with an uppercase letter. So what can we express in first-order logic? Well, let's start with the concept of atomic sentences. So typically, an atomic sentence is either a predicate, like brother, followed by a parenthesis, a left parenthesis, and a number of terms separated by commas with a closed parenthesis. Or an atomic sentence is that term 1 equals term 2. So what's a term? Well, it's either a function with the same syntax as a predicate, or it's a constant, or it's a variable. We can think of terms as being things and predicates as being relations. Why is a function more like a thing than a relation? Well, because a function we can think of as pulling out a part or a characteristic of a thing, which is a thing in itself. So, for example, we can say that if we had a predicate brother, the two terms might be King John and Richard the Lionheart, who were in fact brothers, King John and then Richard I of England. And the idea is to express this relationship that they're brothers. Or another relationship might be that the greater than relationship, and that which is a predicate. And so our predicate is greater than, and the two terms that are being compared by this predicate are the length of the left leg of Richard and length and left leg of our functions against the length of the left leg of King John. Now, those are atomic sentences, and we can create more complex sentences from atomic sentences using connectives. So we could have some sentence S, and a complex sentence from S might be not S, or if we have S1 and S2, S1 and S2 would be a complex sentence, and so forth. And we can express, for instance, implication that way. So, for example, we know, for instance, that if A is the brother of B, then B must be the brother of A. So we can say that this, if we got a predicate sibling, and we say sibling King John, comma Richard, then that implies that sibling Richard King John. Similarly, if 1 is greater than 2 or 1 is less than or equal to 2 is a complex sentence, which actually happens to be true. Another complex sentence might be that 1 is greater than 2 and not greater than 1, 2, and that gives us false and true, which we know to be false. So that brings us to the notion of truth and falsity. So sentences in first-order predicate calculus or first-order logic are true with respect to a model and an interpretation. So the model has to have one or more objects, which are domain elements, and relations among them. Domain elements might be things like kings, for instance, or universities. And the interpretation specifies reference, that is, the things being referred to, for constant symbols, which are objects, predicate symbols, which are relations, and function symbols, which are functional relations. So if you have an atomic sentence, some predicate with some n terms, it's true if and only if the objects referred to by their respective terms are in fact in the relation referred to by predicate. In prologue, this notion of truth is relatively easy in the sense that if, for instance, a relation is defined as a fact, it'll return true, or we can prove it and it'll return true, we hope. So here's an example of a model in first-order logic, and we've got King Richard here on the left and King John here on the right. Now, those of you who've taken English history know that Richard I, or Richard Lionheart, while he was off in France and being imprisoned in Austria and so forth, was subject to a attempted revolt by his brother John, who seized the crown of England. So let's look at what we've got here. So we've got some objects. Richard is a person, and John is a person. John is also a king. We've got the crown, which John presumably is wearing on his head, which is the relation. John is the brother of Richard, and Richard is the brother of John. And there's a function, left leg, and we claim that one leg is longer than another, but note that the function left leg returns a different left leg from Richard than it returns from John. Using this example, let's consider an interpretation in which the term Richard refers to the actual Richard the Lionheart, Richard I of England, and John refers to his younger brother, the evil King John, and brother refers to the relation of being a brother. So under this interpretation, if we see the predicate brother with the terms, the arguments Richard and John, we say that's true exactly in the case where Richard Lionheart and evil King John are in fact in the brotherhood relation in the model. Well, that brings us to the notion of models. Now, it turns out that there are many, many more models typically for any particular knowledge base in first-order logic than in propositional logic. Well, why is that? In propositional logic, we know all the facts, and they can either be true or false, and so we only have two cases for each fact, and so we're going to have some power of 2. It might be a little big, but at least it's not that big. We can, as we've seen in class, we can pretty much draw them all out for reasonable cases. But in first-order logic, because we have variables, these variables can take on basically, well, an arbitrary number of values. So if we have a knowledge base, we can figure out how many first-order logic models there might be. So basically, for each number of domain elements n from 1 to infinity, and for each k-ary predicate p sub k in the vocabulary, k-ary means that it's got k terms. And we saw that in the, for instance, when we defined room 2 the other day, room/2, that remember we said that it had an arity of 2. Well, that's what they mean by k-ary here. Okay, so for each k-ary predicate p sub k in the vocabulary, for each possible k-ary relation on n objects, for each constant symbol c in the vocabulary, for each choice of referent for c from n objects, and so forth. And what's more, what if one of these variables is a number, and even if it's an integer, it could have basically up to the max int value, and in the real world even more, so it's just a lot. So we're probably not going to be doing model checking in first order logic. So that's a little bit of introduction to first order logic and syntax and its meaning. So now we can start looking at how to start writing first order logic expressions with which we can work. And to do that, we're going to need a couple concepts: universal quantification and existential quantification. So syntactically, universal quantification has the for all symbol plus a list of variables to which it applies and some sentence. So for example, and this probably isn't true, but everyone at Berkeley is smart could be represented as for all x at x Berkeley implies smart x. In other words, for all the values that x could take on, if the relationship at x Berkeley holds, then it's also true that x is smart. More formally, we say that for all x, some proposition is true in a model M, if and only if that proposition is true with x being each possible object in the world. In other words, for universal quantification to hold, x can take on every possible value, and the p has to be true for each of those possible values. Now, the idea of universal quantification can be thought of as equivalent to a conjunction of all the possible instantiations of the proposition p. So for instance, if we have objects in our world like King John and Berkeley, then for all x at x Berkeley implies smart x could be seen as conjunction of all the possible instantiations, like at King John Berkeley implies smart King John, at Richard Berkeley implies smart Richard, at Berkeley Berkeley implies smart Berkeley, and so forth. Basically true for all the possible instantiations of the variable. Now, in our programming language that we're going to use, Prolog, the language implicitly uses universal quantification. By that I mean, so let's say we have an expression like for all x and y, brother x and y implies sibling x and y. Well, that's expressed in Prolog as sibling x and y if brother x and y, and the universal quantification, that is, for all x and y, is implicit. When you are using universal quantification, you're normally going to be wanting to use the connective implies rather than something else, especially and. And there is a mistake which you should be able to recognize fairly early on as trying to use and as the main connective with universal quantification. So if you see an expression like for all x at x Berkeley and smart x, it doesn't mean that everybody at Berkeley is smart. What it means is that this is true for all x. So whatever the value of x is, it means that they're at Berkeley and they're smart. So basically it means that for all the possible instantiations of x, everyone is at Berkeley and everyone is smart. So you're going to be smart and use implication rather than and normally when you are using universal quantification. Turning to existential quantification, the syntax is, this should be familiar to you from discrete math, there exists some set of variables that are true in some sense. So for example, and this is probably true, there exists some x such that that x is at Stanford and that x is smart. More formally, we can say that there exists an x in proposition P so that proposition P is true in a model M if and only if P is true with x being some, that is, any possible object in the model. All we have to do is find one value of x for which P is true and the existential quantification is true. And so the likewise, in a way corresponding to our conjunction instantiations for universal quantification, we can think of existential quantification as being a disjunction of all the possible instantiations of P. So in other words, there exists an x such that at x Stanford and smart x is equivalent to at King John Stanford and smart King John, or at Richard Stanford and smart Richard, or at Stanford, Stanford and smart Stanford, and so forth. Now there's a mistake you can avoid here too. So typically we're going to want to use and as the main connective with existential quantification, and one common mistake is to use implications as the main connective with existential quantification. So if you see an expression like there exists an x such that at x Stanford implies smart x, let's think about what that means. So if there's any x for who is not at Stanford, and presumably there are lots of x's for whom that is true, then the implication as a whole is true, right? Because if the premise of the implication is false, then the implication as a whole logically is true, which means that if you say there exists an x such that at x Stanford implies smart x, that means it's true if there's anyone who is not at Stanford, which is probably not what you had in mind in the first place. The good news is that it doesn't matter what order you put universal quantifiers if they're all universal quantifiers, and similarly for existential quantifiers. But if you mix universal and existential quantifiers, then you have to make sure the order is what you mean. So for instance, if you have an expression like there exists an x for all y such that loves xy, what does that mean? Well, it means that there exists some x such that they love all possible y's. In other words, there is some person in the world, there exists some x who loves everyone in the world. Let's try the quantifiers in the other order. For all y, there exists an x such that loves xy. Well, that means that there's lots of possible y's and only one x again, but this time it means that x, everybody in the world, that is y, is loved by at least one person, right? Because there exists, for every y, for all the people in the world, there exists someone who loves them. So we can see that the order of the quantification makes a difference. Now, one cool thing is that universal and existential quantification are related to each other in the following way. So if I have an expression like for all x likes x ice cream, which we could loosely translate as everybody likes ice cream, we could express the same idea by saying, well, there isn't anyone in the world who doesn't like ice cream. And likewise, if I have an expression like there exists someone in the world who likes broccoli, then we can equivalently say that not for all x, right, not likes x broccoli. In other words, it is not true for everybody in the world that they all hate broccoli, thus suggesting, meaning equivalently, that there must be at least one person in the world who likes broccoli. So let's try out our new skills with some creating predicate logic examples with some sentences. So, for instance, how would you express the idea brothers are siblings in a first-order logic sentence? Think about it for a minute. You can stop the video if you want, just to try out your luck, and then we'll come back to it. Okay, so here's what I've got. For all x and y, brother x and y implies sibling x and y. Makes sense, right? How about the notion that sibling is symmetric? Well, that's pretty easy. For all x and y, sibling x and y is equivalent to sibling y and x. You could see that one coming, right? How about this? One's mother is one's female parent. Take a moment to try to work that one out. And here's one way of expressing it. For all x and y, mother xy, that is what we mean is x is the mother of y, is the same as saying that x is a female and that x is a parent of y. On a slightly more complicated concept, how about a first cousin is a child of a parent's sibling? So take a minute or two to figure this one out. And here's what I've got. For all x and y, first cousin x and y is equivalent to saying that there exists p and ps such that p is a parent of x and ps is a sibling of p and ps is a parent of y. One more concept is going to help us, and that's the concept of equality. So here we're going to say that some term 1 equals some term 2 is true under a given interpretation if and only if they both refer to exactly the same object. So while it is true that both King John and Richard I have a left leg, they're not the same object. This notion of equality and inequality, for that matter, enables us to express some slightly more complex relationships. So for instance, here's a more complete definition of sibling in terms of parents. So for instance, we can say, for all x and y, sibling x and y is equivalent to saying that for x not equal to y, and there exists some m and f, such that m is not equal to f, in other words, your parents are different people, and the siblings are different people for that matter, and m is the parent of x, and f is the parent of x, in other words, x shares the parents m and f, and y also shares parents m and f. So let's turn to applying what we know about first-order logic to applications. And needless to say, the application we're going to use is Wumpus World. So suppose we have a Wumpus World agent using a first-order logic knowledge base, and this agent perceives a smell and a breeze, but unfortunately does not perceive any glitter at some time t equals 5. So remembering our control loop of how the agent will work, we're going to tell the knowledge base what we perceive. So we'd say, tell the knowledge base that we have the percept, smell, breeze, and none at time equals 5. And then we'll ask the knowledge base what to do. So we'll ask the knowledge base, is there some action A such that A is the appropriate action at time 5? In other words, does this knowledge base, all the items in the knowledge base, entail any particular actions or action at time equals 5? And just for example, it might say the answer is yes, where the action is shoot. And the expression A/shoot is a substitution. In other words, it shows the variable A is bound to the value shoot. We can represent a similar idea, exactly the same idea, really in Prolog, remembering that in Prolog, relations and terms, constants are lowercase and variables are uppercase. So to tell in a Prolog environment, we use assert z, which adds our new fact or statement to the end of all the ones we know. If we wanted to add it to the beginning, we use assert a. but we'll use assert Z. It's standard practice. And we'll add the fact percept, and then the first argument of percept is a list, stench, breeze, and none. And the second argument is 5, which is the position we'll have for the time. And once we've done the assert, the Prolog interpreter comes back and says true to tell us it's asserted this fact. And then we'll pose the query action, the variable a and 5, basically saying what action do you take at time 5, and if the facts are those that in the knowledge base I came up with shoot, it'll say a equals shoot. And we're done. So in general, in using first order logic and knowledge bases, what this means is that given some substitute sentence S, and a substitution little sigma, S sigma denotes the result of plugging this substitution sigma into S. So for example, if S is a sentence smarter X and Y, in other words, we'll have that mean that X is smarter than Y, and sigma is a binding or a substitution of Hillary for X and Bill for Y, then S sigma is smarter Hillary and Bill, so that X and Y are bound to Hillary and Bill respectively. And in general, ask knowledge base S returns some or all set of substitutions sigma such that the knowledge base entails S sigma. In Prolog, we'd write it this way. Our query would be smarter xy, and you'll note that smarter has to be a lowercase because it's a predicate, and PowerPoint had so helpfully capitalized the beginning of a sentence. Anyway, so our query is smarter xy, and it comes back with the bindings x equals Hillary and x equals Bill. Looking at the knowledge base for Wumpus World, the idea of perception we can represent as for all B, G, and T, a percept of smell, and then whatever the values for breeze and glitter are at some time t implies that the agent has smelt at time t. Okay? And the only thing we can smell is the Wumpus. And similarly, if we're going to perceive the gold, for all S, B, and T, having a percept of S, B, and glitter at time t means that we're at the gold. We're in the same square as the gold. So we could build in a reflex that says anytime we're at the gold, we pick it up. But the problem with that is that we might already have the gold, and all we do is keep picking up the gold we already have. So we can have a reflex with an internal state. That is, we'll check to see if we have the gold already. So this would be a little more sophisticated. We say for all t, that is at all times, if we're at the gold at time t and we're not holding the gold at time t, then we grab the gold. Okay? Now, holding the gold is not some property of the world. It's not something in the maze. It's something that is a result of what we have done. So that means that keeping track of change is essential, and we're going to have to tell our knowledge base that we are holding the gold at time t. Otherwise, when we grab it, otherwise we'll keep grabbing the gold. Now, not everything in the knowledge entailed by the knowledge base is a sentence in the knowledge base. We're going to be able to deduce things. So we could deduce, for instance, that if for all x, and that's location, and all t times t, if our agent is at x at time t, and the agent has smelt at time t, then we can say that location x is smelly. And likewise, we can say the same thing about breezes and breezy. How do we represent this in Prolog? Well, we would say that location is smelly, that is, there's some predicate smelly, and the argument will be some variable loc, standing for location, if it's true that the agent is at that loc at some time and they've smelled something at that time. And then likewise, that location is breezy if the agent is at that location at the time and it's breezy at that time. Now, squares are breezy near a pit, so we can infer the cause from the effect. In other words, we could have something that diagnoses why we have the breeze. So what we'll say is, if we, for all y, if it's breezy, then there must exist some pit in location x such that location x is adjacent to our current location y. Conversely, if we know that there is in fact some pit, we can deduce that the adjacent locations must be breezy. So for instance, if we could say that for all x and y, if there's a pit at location x and x's location is adjacent to y, then we know that y is breezy. And in prologue, we can do the latter one, because remember, horn clauses can only have one conclusion. So we can say location is breezy if there's a pit at some pit location and our loc is adjacent to the pit location. Neither of these rules, unfortunately, is complete. It doesn't say, the causal rule, for instance, doesn't say whether or not squares far away from pits can be breezy. It's possible. So a more complete definition for breezy would be the following predicate. Well, for the breezy predicate would be something like, for all y, location y is breezy is equivalent to saying that there exists an x such that there's a pit at x and x is adjacent to location y. Now, I've rather glibly mentioned time as one of the arguments, and time presents a lot of issues in artificial intelligence and in first-order logic. The issue, of course, is that facts aren't true forever. Sometimes we're holding the gold and sometimes we're not. Sometimes the wumpus is alive and sometimes it's not. Sometimes we're in square 2-1 and sometimes we're in square 3-3. Things change. So we need to be able to represent what our current state is as opposed to what a universally true state would be. And the situation calculus is a way to represent change in first-order logic. It adds a situation argument to each non-eternal predicate. So we'll add holding gold now denotes that situation where now is some time, namely now. And these situations are connected by the result function. So we say that the result of action A is the situation so result A of S is a situation that results from doing A in situation S. In other words, result AS is a new situation, and it's the successor situation to little s. How do we keep track of all this? So we could have an effect axiom that describes changes due to action. So we could say for all s, at gold s implies holding gold as a result of grabbing s. In other words, this second part was result of some action at some time, and the new result is going to be holding gold at this situation. And that's a way of describing what changes. Another approach would be to describe what doesn't change. So we could say for all s, we have arrow in a situation s if we have the arrow in the situation where result is grab. It was a grab. Because we haven't shot the arrow, we've grabbed the gold instead. Now, there's a very famous issue in AI called the frame problem. And the problem is to find an elegant way to handle non-change. Just because we've grabbed the gold, we need to be able to understand that nothing else in the world has changed. So what we want to do is, in our representation, try to avoid frame axioms, because if we had to have a frame axiom for every possible action, we'd have a ton of them, and we spend all our time reasoning about what hasn't changed instead of doing useful computation. And we want to have an inference approach that avoids repeated copyovers. In other words, keep repeating, it was true in the previous state and now it's true in this state. Likewise, there's something called the quantification problem. And what we want to do is avoid the issue or deal with the issue that real actions, the real world, require endless caveats. For instance, what if we try to grab the gold but somebody put grease on it, or it was nailed or screwed down to the floor of the maze? Okay? And the other problem is the ramification problem. That is, real actions, the real world, have many secondary consequences. I mean, what if there's dust on the gold and we scatter that? Or there's wear and tear on our gloves and we have trouble picking it up later on, and so forth. One way to describe actions is to use successor state axioms, and they solve this representational frame problem. So each axiom is about a predicate, not about an action. The idea is that P is true after some action is equivalent to saying that an action made P true, or that P is true already and no action made P false. So for instance, here's a successor state axiom for holding the gold. For all actions S in A in situations S, holding gold as a result of A and S is the same as the action equals grab and at gold S, or we're holding the gold at S and we haven't released the gold. Another issue in first order logic is making plans. So let's say that our initial condition in the knowledge base is that our agent is at 1, 1 in situation 0, and in situation 0 the gold is in 1, 2. So now what we want to ask is, ideally we'll want to know, is there a situation S such that we're holding the gold in that situation? And ideally, we'll come up with a set of situations that are the results of applying actions to predecessor situations. And here the answer would be, in this circumstance, because it's easy, that the binding of S would be the following set of situations. That is, where we grab in the situation that's the result of moving forward from the initial state. So in other words, go forward and grab the gold. And of course, this assumes the agent is interested in plans that start at S0, and that S0 is the only situation described in the knowledge base. Otherwise, we might have multiple results. How would we describe that in Prolog? Well, we could say something like, okay, we want to be holding the gold in some situation which I've called the variable of the situation, and it gives us the binding of the situation that is the result of grabbing in the situation that's the result of moving forward. And note, this is a variable situation and not the gentleman from Jersey Shore. Okay, so there's a better way to make plans because these nested situations could go very long and be very difficult to read. And instead of looking at nested situations, we'll look at plans as action sequences. So action 1, action 2, and so forth is in a list. And where the plan result PS is the result of executing P and S. So in this case, when we ask the query, is there a P that gets us to the situation of holding the gold in the plan result that starts with the initial situation will come up with a binding where the action sequences move forward and grab the gold, which makes sense. So we can define plan result in terms of result. So for all situations S, plan result of the empty list and S is S. In other words, that's where we're starting. And for all A, P, and S, the plan result of some action A followed by a tail list of actions P, that is more plan. So A is a single action and P is the tail of the list that could be 0 or more actions. In some situation S is plan result of P and the result of A and S. And planning systems are in fact special purpose reasoners designed to do exactly this type of inference more efficiently than a general purpose reasoner. So we could show this kind of approach in Prolog as saying, as making the query holding the gold in plan result plan S of 0, and it comes back with the binding for our action plan, move forward and grab the gold. So what have we looked at today? We've looked at first order logic, and we noted that objects and relations are semantic primitives, and we looked at the syntax for first order logic, namely constants, functions, predicates, equality, and quantifiers. And we noted that first order logic has better expressive power than propositional logic, and in fact it is sufficient to define Wumpus world. And we looked at how to express states and change, and we did so in terms of situation calculus. So we talked about conventions for describing actions and change in first order logic, and we showed how we can formulate planning as inference on a situation calculus knowledge.